Hey everyone, and welcome. I am absolutely thrilled to have you here for this explainer. Today, we're going to take what might normally seem like a dense, maybe even slightly intimidating engineering topic, and transform it into a really thrilling, vibrant roadmap of the physical universe. We're talking about fluid mechanics. And, whether you realize it or not, the principles we're about to explore govern almost everything moving around you, and literally everything moving inside you. My main goal today is to give you a clear, structured framework to really understand this incredibly fascinating subject. Think about a sudden splash of water for a second. It's this wonderfully dynamic, beautifully chaotic moment frozen in time. I love starting with that mental image because it instantly grounds the highly abstract math and science we're about to discuss into a totally familiar, real-world reality. Because fluid mechanics isn't just a bunch of numbers on a page, right? It's the physical reality of water crashing, rivers flowing, and waves breaking. We all intuitively understand what a splash is, but today we're actually going to understand the underlying rules that govern it. Okay, let's dive right into our roadmap for today. First, what exactly is fluid mechanics? Second, physicists versus engineers. Third, solids, liquids, and gases. Fourth, measuring the fluid world. And finally, a universe of applications.
All right, part one. What is fluid mechanics?
So by definition, it's simply the study of the flow of fluids. But here is a truly fascinating secret about this whole field. As brilliant as modern science is, our purely mathematical ability is actually too limited to tackle the incredibly complex problems of real fluid flows just on its own. Because of the sheer chaos and the intense variability of moving fluids, we literally cannot rely on equations alone. Whether we're trying to understand the basic physics of the universe or build a massive industrial machine, we have to depend heavily on real-world experimental observations just to test our mathematical analyses. So it's really a science built on watching the physical world very, very closely.
Moving on to part two, physicists versus engineers. Now, what's really interesting here is the clear dichotomy in how this knowledge is actually applied out in the world. On one hand, you have physicists. Their primary drive is really about understanding phenomena. They look at the world and basically ask, why? Why do atmospheric waves form? Why does a fluid that's heated from below suddenly break up into these intricate cellular patterns? Why exactly does a tennis ball hit with heavy topspin suddenly dip so sharply over the net? Then, on the other hand, you have engineers. Their main interest is all about application and solving practical industrial problems. Aerospace engineers use fluid mechanics to design airplanes with low wind resistance and massive lift. Civil engineers use it to design massive dams and huge irrigation canals. Basically, they take the why and use it to build the how.
And this difference in perspective has actually led to some pretty fun historical banter over the years. The famous English pure mathematician G.H. Hardy once joked that applied mathematics is basically just a form of glorified plumbing. Now, obviously, a pure mathematician might look down on experimental science a bit, but as we've just learned, the physical world is way too complex to be captured by elegant pure math alone. Sometimes you just have to get your hands wet, literally.
All right, part three, solids, liquids, and gases.
Let's start by looking at a solid. The defining characteristic of a perfectly elastic solid is that it has what we call a preferred shape. So if you apply a shear force to it, imagine just pushing the top of a thick rubber block sideways, it's going to deform. But the very second you remove that external force, the solid naturally snaps right back, relaxing into its original preferred shape. It essentially remembers what it's supposed to look like. And furthermore, solids can easily withstand both pushing forces, which is compression, and pulling forces, which is tension.
So, the crucial point here is how this completely contrasts with a fluid. A fluid, it doesn't have any preferred shape whatsoever. If you apply a shear stress to a fluid, it doesn't just deform a little bit and wait to bounce back, it continuously deforms. It flows. It yields entirely to the force. And unlike those solids, fluids generally only support compression or pressure stresses. They really don't like being pulled apart in tension. That continuous yielding to shear stress, that is the very essence of what makes a fluid a fluid.
And this brilliantly illustrates the final major distinction we need to make today: the two specific classes of fluids, liquids and gases. While they both flow continuously under shear stress, they handle their boundaries in very different ways. A liquid's volume just doesn't change very much. If you pour a liquid into a large container in a gravitational field, it settles right at the bottom and forms a distinct, free surface that separates it from the vapor above it. A gas, on the other hand, is completely unconstrained. It will absolutely always expand to completely occupy the entire volume of whatever container you put it in.
Okay, moving to part 4, measuring the fluid world.
To make sense of all this, we use a universal vocabulary that's shared by all those physicists and engineers we talked about earlier. We rely on the International System of Units, or the SI system. We have our standard base units, right? Length in meters, mass in kilograms, time in seconds, and temperature in Kelvin. And from those basic building blocks, we derive the critical measurements of fluid mechanics. Force is measured in newtons, and pressure, which is really just force applied over a specific area, is measured in pascals. By strictly adhering to these exact units, scientists all across the globe can seamlessly share their findings without any confusion.
But here's the catch with this stuff. Fluid mechanics involves scales that are sometimes unbelievably tiny and other times massively planetary. Writing out huge, endless strings of zeros gets really cumbersome really fast. So to keep our math clean and focused, we rely heavily on standard prefixes. We use mega for millions, kilo for thousands, all the way down to milli and micro for those microscopic scales. It's a super simple system, but it ensures that the math remains accessible, whether we're calculating the tiny flow through a capillary vein or the crushing pressure of a massive tidal wave.
And finally, part 5, a universe of applications.
Let's actually look at how these concepts scale up to those planetary levels. The exact same basic rules of density, pressure, and fluid flow allow us to analyze surface gravity waves out on the open ocean. We can mathematically approximate exactly how deep water behaves compared to shallow water right near the shore. We can predict crazy phenomena like the hydraulic jump, or even understand those completely invisible internal waves that are moving deep down within the stratified layers of our oceans. It's literally planetary-level engineering.
Now let's move into the digital age and see how this builds. Because honestly, the experimental math is just so incredibly tough, we lean really heavily on computers. Computational fluid dynamics, or CFD, pushes the absolute boundaries of modern engineering. By using insanely powerful computers to essentially slice fluid spaces into millions of tiny grids, we can simulate incredibly complex flows. This allows us to test virtual airplanes, experimental cars, and massive weather systems before they ever even exist in the physical world. It's a total game changer.
And hey, remember, fluid mechanics isn't just about water. It completely dictates the invisible airflows all around us. The principles of aerodynamics explain things like the Cuddy condition and exactly how airfoils generate the lift required to conquer gravity. But it's not just our human-made machines either. These exact same fluid dynamics perfectly govern the propulsive mechanisms of a fish swimming against a strong current or a bird soaring effortlessly on a thermal updraft. Nature mastered fluid mechanics way before we did.
Finally, let's bring this explainer full circle to something deeply personal: biofluid mechanics. The exact same laws of physics, the exact same equations for pressure and continuous deformation we've been talking about, well, they dictate how blood pumps through the complex, winding circuitry of your own heart and blood vessels. Those same rules explain how water travels from the deep, hidden roots of a plant all the way up through its thinnest, highest stems. Fluid mechanics is, quite literally, the science of life itself.
So, to kind of synthesize our entire journey today, everything we've discussed, from defining what a continuous deformation under shear stress actually is, to differentiating liquids from expanding gases, to the universal SI metrics we use to measure it all applies universally. From the aggressive dipping topspin of a tennis ball to the massive churning weather patterns of our entire planet, fluid mechanics truly is the hidden software running the physical universe.
I want to leave you with a really provocative, almost mind-bending philosophical question directly from the text we explored today. It's called the continuum hypothesis. We know for a fact that matter is truly just billions of discrete, highly chaotic, bouncing molecules constantly colliding at microscopic scales. So how is it possible that we can predict its gross behavior in macroscopic forces so flawlessly? How does microscopic chaos somehow create macroscopic order? Think about that for a second the next time you see a perfect wave crashing on the beach. Thank you so much for joining me on this explainer. Stay curious out there, and I'll catch you on the next one.